Dear students, good morning. So good afternoon. Okay, today we'll continue from where we have left yesterday. Okay. In our last class, we are discussing about antenna theorems. Okay. Can anybody tell me what are the three theorems we have studied yesterday? Okay, your voice is not clear. Okay. We have studied three theorems are there. First one is equality of directional pattern, right? Equality of directional pattern. What is the other name for directional pattern? Can anybody tell me? What is the other name for directional pattern? Yes.
Radiation pattern.
Yeah, radiation pattern is nothing but the directional pattern. Okay, what does this theorem explains? What do you mean by equality of directional pattern? Can anybody tell me in your own words? Okay, no problem, please.
A radiation pattern must be same for receiving and transmission of antenna.
Very good, very good. Simple definition. Okay, for transmitting antenna, receiving antenna, okay, the directional pattern or radiation pattern should be similar. Okay, that is the first theorem. And second one, what is the second one? What is the second theorem?
Equality of antenna impedance.
Equality of antenna impedance. Antenna impedance plays very important role in designing antenna systems. Why? Because the electromagnetic radiation which is coming from the antenna, it has to be transmitted through the free space. Okay, the antenna impedance and free space impedance should be matching. There should be a matching in the impedance. Okay, similarly for transmitting antenna or receiving antenna, the antenna impedance is also same. Okay. Okay, what is the other? What is the third theorem? What is the third theorem?
Equality of effective height or length.
Equality of effective height or length. Can you explain what is that?
The effective length of transmitting antenna is must be equal to the effective length of the receiving antenna.
Yes, the effective length. What is the units for effective length? What is the units for effective length? Yes. What is the equation for effective length? Can anybody tell me? What is the equation? Equation for effective length or effective height? Okay. Effective length or effective height. Both are same. Okay.
H is equal to V by E.
Yes, yes. H is equal to V by E. What is V? What is the units for V? Units for
Voltage
V.
V.
Voltage. Okay, the units for voltage is volts. And E. What is E? What
Field
is E?
strength.
Field strength or electric field intensity or electric field strength. What is the units? What is the units for E? What is the units for electric field strength or electric field intensity? Yes, you have studied much about this electric fields.
Volts per meter.
Very
Volts
good.
per meter, sir.
Volts per meter. Very good. Very good. Okay, I'm hearing only answer from you, Amma. Rest of the people also you have to answer. Why so many very less attendance? Only 26 members are attending the class. Okay. The what is the unit for effective height?
Meter square.
Meter square. Height you can measure in meter square.
Meter, sir.
Meter. Volts divided by volts per meter. That is equal to meter. Okay. Can anybody tell what is this equality of effective height or effective length? What is this theorem says? What is this theorem
Effective
says?
height must be equal for both transmitting and receiving of antenna.
Simple. Okay. The effective length or height of a transmitting antenna or receiving antenna should be same. Okay. Very good. These are the three theorems. Okay, especially this impedance, antenna impedance. Okay, in our second unit, okay, we will derive the antenna impedance for different types of dipole antennas. Okay, we will see more details about some of these theorems there also. Okay, we'll continue our discussion. Now our next topic is fields from an oscillating dipole. Okay, earlier also we have discussed this topic. Okay, how electromagnetic waves are generated from an antenna? Can anybody explain me how electromagnetic radiation or electromagnetic waves are coming from an antenna? How can you explain this phenomena, electromagnetic waves? How electromagnetic waves are generated? Can anyone? You already know about these things. Okay, in our basic classes we have discussed more about how these electromagnetic waves are radiated from an antenna. Can anybody tell me how the electromagnetic waves are coming from an antenna? What is the main source of this electromagnetic energy?
Oscillating the charges.
Very good, very good. Oscillating
Oscillating
charges.
the charges.
Which charges are oscillating? Which charges are oscillating? Where these charges are there actually? Yes, yes, please.
Conductors.
Yes, antennas are made up of conductors. Conductors are having free electrons.
Electrons.
Yes, free electrons. Electrons are having, electrons are called, they have a packet of energy. Okay, by accelerating and deaccelerating these electrons, okay, there is a tremendous amount of energy is radiated in the form of electromagnetic radiation. Okay, here we will discuss about a simple oscillating dipole. Okay, what do you mean by dipole? Earlier also you have seen dipole means you are having two poles or you are having two conductors. Okay, in those conductors we will apply a sinusoidal signal. Sinusoidal means one is positive voltage, other one is negative voltage. Okay, here we are applying the sinusoidal signal to these two two conductors. Okay, they will emit the electromagnetic radiation. Okay, we'll see, we'll take a one simple uh, example and how these electromagnetic field lines will be generated. Okay, how they are disconnected from this antenna and how they will travel from antenna to the different parts of the earth or towards the receiving antenna. Okay, here the dipole has two equal charges of opposite sign. Okay, it has two equal and opposite charges. They are oscillating in a harmonic motion. Okay, we'll see this. Okay, before that I want to see how these electromagnetic waves are generated. Here you can see here is a small infinitesimal length of a wire. Okay, in this wire we are having two equal and opposite charges are there. Okay, for our understanding purpose, here we are drawing only one electric field, one field line, electromagnetic field line. Okay, generally there are n number of electromagnetic field lines will be there. Okay, for our understanding purpose, okay, here we are showing only one field line. Okay, field line, it generates these are the two equal and opposite charges. Okay, right? Okay, we'll see in detail in our next slide. Okay, see here the radiation coming from an oscillating electric dipole is shown here. In this we'll discuss in detail every stage of this figure. No? Here let us assume and t is equal to 0. Okay, we are having two equal and opposite charges. Okay, here we are having a light blue color and other one is green color. Here let us say, can anybody tell me which is the positive charge and which is the negative charge? Now, by seeing this figure, can anybody tell me which is the positive charge and which is the negative charge? Here we are having green and we are having blue charges. Can anybody guess?
Blue is positive.
Blue is positive. Why? Because the field lines The electric field lines are coming from the positive charge to the negative charge. This is the direction. Okay, here let us say this is the maximum length of the wire. Okay, okay, and at t is equal to 0, these two charges are maximum distance apart. Okay, let us say this is positive charge is here and negative charge is here. Okay, these charges are part, okay, distance apart. Therefore, the current is minimum. Or let us say the current is 0. Okay, when the current is 0, at t is equal to 0, okay, there is a field line. Here we are showing only one field line, but in practical there are so many field lines are there. Okay, here the field lines which is started from this positive charge and it is terminating at the negative charge. Okay, here this is called the wave front. Okay, when these two charges are apart, there is a wave front just initiated. Okay, it is just initiated. Now let us assume these two charges are coming towards each other. Let us say when time t is equal to 1 by 8 times of t. What is capital T? Here we are assuming that these two charges are in harmonic motion. Okay, the total time period for starting this charge and going here and return to this same position, we are considering it as a one time interval or time period. Okay, in simple harmonic motion, okay, we'll consider one total cycle. Cycle means here the charge is started here, it will go here and it will come back here. It will take totally, it will take the time duration is capital T. Okay, let us assume when time t is equal, when time t is equal to, okay, time period by 8, 1 by 8 time of the time period. Let us say this positive charge is moving towards the negative charge moving towards positive charge. Let us say now these two are coming here. Now there is some current increase in this, okay, in this conductor, and the wave front will start expands. This will expands. These field lines are same direction only. Okay, now they are starting from the positive charge and they are terminating at the negative charge. Similarly, at t is equal to 1 by 4 times of t. Okay, 1 by 4 times of t means it will travel the quarter the wavelength. Okay, quarter the wavelength means, see, it will come to the middle of this wire. Okay, at the middle of this wire, let us clearly observe that these two charges, they will cross each other. Okay, while crossing these two charges, there will be a crossing of this electromagnetic field lines. Because of this crossing, these field lines will be disconnected from the antenna, or separated from the antenna, and they will move apart. Let us see here, when time t is equal to 3 by 8 times of the time period. Okay, see here, these two charges, now the negative charge is coming this side and positive charge is coming the other side. Okay, let us see here. Here the wave front, whatever the generated, this is the electromagnetic wave front, it will be separated from the antenna and it will move away from this antenna. At the same time, okay, because of these two charges, there is another wave front will be started at t is equal to t by 2. If you see, at the time t is equal to t by 2, okay, now the positive charge is coming this side and the negative charge is coming this side. Now let us see the direction of the field lines. How is the direction of the field lines? Now it is the positive charge here, blue one. Here is the green line, it is the negative charge. Now the direction of the electromagnetic field lines are just comparing this t is equal to 0 and t is equal to 1 by 2t, they are just reversed. Okay, in this manner, if you can able to swap these two opposite, equal and opposite charges, okay, we can able to generate the electromagnetic wave fronts. They are at every crossing of these two charges, these electromagnetic lines will be separated and they will travel away from the antenna. Emma, how have you understood this concept? How this oscillating dipole will generate electromagnetic waves? Okay, is there any confusion? Hello, here we can see clearly. Okay, okay. Let us consider a dipole antenna with two equal and opposite charges oscillating up and down in simple harmonic motion as shown in the figure. Okay. See here, I have given the note here. For better understanding, we will analyze the electric field by taking a single electric field line. This is the assumption. Why, sir, we have drawn only a single line? Okay, this is for our understanding purpose only. We are drawing a single electric field line. Okay, let T be the time period of the oscillations. Okay, here this is not small t, this is capital T. This is not here, this is the small t, it's not small t, this is capital T. Okay, here this is the time period of oscillations. Time period of oscillations. Let at a time t is equal to 0, the two equal and opposite charges are at maximum separation. Maximum separation, because of the maximum separation, okay, it carries only minimum current or zero current. Current is zero. Okay, at this position, the electric field lines, they will start at this positive charge and they will be terminated at this negative charge. Okay, here we are drawing only one line, but there are so many lines will be there in practical case. Okay, here the wave front just initiated. What is this wave front? This is the electromagnetic wave front. Okay, similarly at t is equal to capital T by 8. Okay, this is the quarter wave. This is the T by 8 means, okay, small amount of the time period. Okay, here you can see that this positive charge is coming here and the negative charge, it travel from this point to the this point. Now this wave front starts expands. Okay, because of these charges are very near, there is a little amount of current also will increases. Okay, because of the current increases, this wave front will expands. Okay, at time t is equal to t by 4, here also this is capital T, here this also capital T by 4, capital T by 4. Okay, these two charges are coming to the center of this line. Okay, and after next moment, they will try to cross each other. They will try to cross each other. During that time, the field lines will be break from the dipole, or the field lines will be separated from the antenna because of this crossing. Okay, they will be separated and they will move away from this antenna. Okay, see here. Okay, in our next slide, after the time period t is equal to 3t by 8, the field lines are completely separated and released from the dipole. Okay, these are the electromagnetic wave front. This will be completely separated from the antenna and it will travel, it will move away from this antenna. At the same time, there is a because of this positive charge and negative charge, there is a initiation of another wave front. Okay, there is another wave front. The direction of the field lines are from positive to the negative direction. Okay, after some time, after t is equal to t by 2, t by 2 means positive charge is coming to this end and negative charge is coming to this end. Okay, now, okay, see, this wave front is already, it is expanded and it is moving away from the antenna. At this stage, okay, there these two opposite charges are reaching the maximum distance. So this carries very little amount of the current or zero current. Okay, and this process will continue if these two charges are oscillating in a simple harmonic motion. These electromagnetic waves will be, the wave fronts will be first generated and they will be separated and they will move away from the antenna. Okay, this about the fields from an oscillating dipole. Okay, dipole means two poles. Here, for our convenient, we are assuming that there are two equal and opposite charges. They are oscillating in a simple harmonic motion. Okay. Any doubts in this? Any doubts? until so far? Have you understood this concept? Hello. Now, shall I continue next topic, or we want to? You have any doubts? Are you able to listen my voice?
Yes, sir.
Okay, Shashita, you have any doubts?
No, sir.
Okay, this already we have discussed, right? This topic here, we can more clearly you can understand how these electromagnetic waves they will be generated and how they will separate it from the antenna, and how they will move from this antenna towards the receiving antenna. Okay, our next topic is antenna field zones. Okay, earlier I have mentioned that the antenna surrounding area is divided into two types. One is far field, another one is near field. Okay, and also we have made some assumptions also while calculating the radiation pattern. There also for electric field intensity, okay, E we have taken only theta and phi. That time also I have mentioned that, okay, whenever you are measuring the field strength or drawing the radiation pattern in far field, you have to consider only theta and phi. If it is a near field, okay, there you have to consider both r, theta and phi. Have you remembered that point, Sashvita?
Sir?
Have you remembered that point? While drawing the radiation pattern, there I have said that in spherical coordinate system for electric field intensity, you are writing E of theta gamma phi. Okay. In spherical coordination system, we are having r theta phi, right? Why that r component is missing? I have explained there. Have you remembered that? You have not remembered? Okay, no problem. Okay, here this is our antenna. This is the this is our antenna. Let us assume it is a dipole antenna. Di means two. Here it is having two conductors. Okay, this is a just is a boundary sphere. Okay, boundary sphere. Let us assume D is the length of the antenna or diameter of the antenna. Both are same. Okay. Okay. Are you able to listen my voice?
Yes, sir.
Okay. Let us assume we are having a simple dipole antenna. Dipole means two conductors is there. Okay. Here we are drawing a sphere. Okay. An imaginary sphere. Actually, we have drawn in a solid sphere. Actually, this is an imaginary sphere. Okay. Here the diameter of the sphere is D, or D is also called as the length of the antenna. This is the length of the antenna. Okay. The distance, okay, the distance from this antenna, okay, to this circle. Okay, what is this circle? Here, this is the circle. Circle. It's not a circle. It's also sphere. Okay, it's a antenna means antenna will radiate the electromagnetic waves in three-dimensional. So here, this is the radius of the sphere. Okay, let us say if r is equal to 2 into d square by lambda, what is d? D is the length of the antenna or the diameter of the antenna. Okay, if the r less than 2d square by lambda, that region is called near field. Okay, this near field also named after a scientist, Fresnel region. Okay, we are as a electronics and communication engineer or antenna engineers. Okay, we are most interested about this far field. Why? Because our antenna is located in far field. Okay, near field we are not much bothered about the near field. Okay, this nobody interested to measure the electric field intensity in the near field. Why? Because this is very close area from the antenna. Okay, the region which is the radius of the sphere greater than 2d square by lambda, it is called far field or Fraunhofer region. You have to remember these two terms. Near field is also called as Fresnel field, and far field is also called as Fraunhofer region. Fraunhofer region or Fraunhofer zone. Okay, we are interested in this far field region. Okay, whenever we are measuring the electric field intensity or normalized power density, okay, we consider the only the theta component and phi component. In far field means R is equal to very large. Okay, in those at those points, if you want to measure the radiation pattern, okay, we will consider only theta and phi. Okay, we don't we omit the R. Okay, after 10 minutes this will be disconnected. Please try to rejoin the session. Okay, this is the field zones antenna field zones surrounding the antenna. Okay, one is near field or Fresnel field. You have to understand, you have to remember these two terms. the other one is the other one is far field or Fraunhofer region. Okay, you have to, what is the condition, what is the minimum range. Okay, if you want to measure the radiation pattern, that minimum range should be R is equal to 2d squared by lambda. After this range only, you can measure the radiation pattern. Okay, this is the boundary condition, or this is the boundary sphere. Okay, from here that far field will start. Okay, that's only how here I have mentioned this point. See here, near field region or Fresnel region, far field region or Fraunhofer region. What is capital D? Capital D is the antenna length or diameter of antenna. Okay. In near field, what is the condition for near field? In near field region, it is the zone at which, okay, the distance are less than the distance are less than 2d square by lambda. What is lambda here? Can anybody tell me what is lambda, students? What is lambda? What is lambda? Here, R is equal to 2d square by lambda. What is lambda? Yes, can anybody in the class?
Wavelength.
Yes, wavelength. Lambda is the wavelength of the electromagnetic waves. Okay. Okay. For near field, R should be less than 2d square by lambda. For far field, R greater than 2d square by lambda. Okay. The condition for measuring the radiation intensity or radiation pattern, okay, the R value, minimum value, R value is equal to 2d square by lambda. That is the minimum value. Maximum, it can extend up to infinity. It can extend up to infinity. Okay. This is the condition. You have to remember this formula. R is equal to 2d square by lambda. Okay. Okay. For in this connection, we'll try to solve two problems. Okay. First of all, note down the first problem. Note down the first problem. Calculate minimum distance required to measure the field pattern of antenna of 2-meter diameter at a frequency of 3 gigahertz. Okay, we'll try to solve this problem. Come on, note down. All of you have to note down in your notebooks. You have to note down this problem. Calculate minimum distance required to measure the field pattern of antenna of 2-meter diameter at a frequency of 3 gigahertz. First, note down the problem. Note down the problem. What is the minimum distance required to measure the field pattern? Field pattern of antenna. What is given? First, note down what is given in the problem. What is given in the problem? Can anybody tell me? The diameter, the diameter of an antenna is equal to 2 meters. Capital D is equal to 2 meters. Next, frequency F is equal to 3 gigahertz. F is equal to 3 gigahertz. Now, what is the equation for minimum distance required to measure the field pattern of antenna? Now, can anybody tell me what is the equation? What is the minimum
Is
distance?
equal to 2d square by lambda.
Very good. Now, note down the minimum distance required to measure the field pattern of an antenna is capital R. Capital R is equal to 2d square by lambda. Very simple. What is the value of lambda here? How to calculate the value of lambda? How to calculate the value of lambda? Wavelength. Frequency is given, right? You know the frequency. Frequency is equal to 3 gigahertz. Okay, if you know the frequency, you can easily find out the wavelength. What is the equation for wavelength? What is the equation for wavelength? What is the equation for wavelength? Now, what is the equation for wavelength? Can anybody answer my question? What is the wavelength? What is the equation? Nobody is answering my question. Hello. No, are you right? Are you solving the problem or doing something else? Shashwita, are you there?
Yes, sir.
Have you solved the problem?
Solving, sir.
Try to solve the problem. Very simple problem. If I show the answer, it is a very easy question only. Boys, who else are doing? All are doing or not? Naveen? Or Naveen? What is the answer? Shivakumar? Akila? Shilpa, are you doing? Have you solved the problem, Shilpa?
సార్ లేదు సార్ చేస్తున్నా.
Tell me what is the value of lambda? If you know the lambda value, you can easily calculate the R value. R is equal to 2d square by lambda. Okay, you already know the value of D. D is equal to 2 meters. Okay, only thing is you have to calculate the wavelength lambda. You have to calculate the wavelength lambda. Anyone in the class who calculated the value of lambda? Let me know. No, nobody calculated the value of lambda. At least give me a try. What is the relationship between frequency and wavelength? Shashwita?
Lambda equal to C by F.
Yes, C by F. What is C? What is C?
Speed of the light.
Speed of the light 3 into 10 to the power of 8 meters per second. Okay, make all the units that are in meters. Okay. Tell me the value of wavelength lambda. Then I will show you the full solution. Now that meeting will be disconnected in a few seconds.